record, and we are back on the air. So we did part B, we figured that out. Part C, I'm given IC and IE. I could really quickly find IB because I have two currents, find the third. And then I could calculate beta, and then I could calculate alpha. Part D, I'm given two currents. I find the third with KCL, find beta as IC over IB, and then I can find alpha. Okay. So there are these other modes of operation. We've talked about active a lot. In the active mode, VBE is positive and VBC is negative. So this is positive axis, this is negative, positive, negative. That is the active mode. Now, the other mode, I'll talk about first, is I could go through and forward bias the base collector and reverse bias the base emitter. It should work just the same, right? Except that we built this non-symmetrically. So reverse active does work like an amplifier, but it works like a bad amplifier. This is analog. And one of the things you can do, and that when I was actually teaching a lab class that we used BJTs in, you could pretty much tell when somebody got an amplifier and their gain wasn't right. First thing that you checked is you went back to the data sheet and you said, which leg of the transistor is the base, which is the collector, and which is the emitter. And sure enough, they usually had them swapped. If it was acting like a switch, then it was one of the other regions of operation. Okay. Now, if I reverse bias both these regions, I have two reverse bias diodes. I've got a really good cutoff. Almost no current flow. It has to flow through two reverse bias diodes. If I forward bias both, and we use this in the digital, would be my digital off state. If I want to have the digital on state, I use this region here called the saturation, where I'm basically forward biasing both of my diodes. And a series pass transistor is just a transistor switching between digital on and digital off, much like that inverter, that NPN inverter you saw in the lab last week. That's a really useful circuit. So four modes of operation. Oh, good. Thank you. Yeah, it acts like an amplifier, but its gain isn't very good. Yes. I mean, sometimes the gain is really bad, like the gain's less than 1, depending upon your transistor and how you have it biased. Okay. Okay, good. I think you got it. Yes. Okay. So I've got models of the transistor in the 3 different regions. This is my favorite. This is cutoff. I went ahead and labeled them. In cutoff, no current flows, or just leakage current, and that leakage current can be like attoamps. Most people don't care, but astronomers. IC0, IE0, IB0, and the transistor just looks like a big open circuit. I'll tell you, this was the trick that made me survive Begensky's class. Great. If a transistor is on, the first thing you always assume for hand calculations is VBE is 0.7 of a volt. Whether it's in saturation or active, that's always true if it's on. When we, you know, like in the lab, when we measured the diode drops, we found they were more like 0.6 or 0.8 volts, but they were around 0.7. The 0.7 is an approximation, but it's the best one you can do, and it will make it so you can actually solve these circuits. Now, the other thing is for the digital circuits, when I have a digital on, this VCE is pretty low, and it's always around 0.2 of a volt. So if I tell you the transistor's in saturation, you automatically know two voltages. You know VBE and you know VCE. If it's inactive, you know VBE. And the active region is where you have this relationship with beta to the current. In the saturation, you don't get to use those equations, but you get this added bonus of you know what VCE is. And what I would do on one of Bagensky's tests, and they were horrible, he typically failed about 2/3 or more of the class, is I would write down, if I knew it was in saturation, if it was a digital circuit, I'd make all my VBEs 0.7, I'd make my VCEs 0.2, and then I'd figure out the rest of the circuit. And that was the thing that got me through it. If it's an active, if it's an amplifier, then I know VB is 0.7 and I know the relationship between the currents. Oh, I'm just, pen isn't working. And now pen works. Wow, I figured that out after only, what, a semester and a half. Okay. Yes, it's too close to finals. My cognitive load's gonna be low. I'm relaxed. All I did today was actually write practice finals and go to lab meetings. Those are fun. So this is an example circuit. Okay, so the first thing it says is that it is in active mode. So in active mode, I know VBE is 0.7 of a volt. I don't know anything about VCE, but I do know that IC equals beta IB. And we're given beta. So what do we know here? Okay, so we know the emitter's at 0 volts because it's tied to ground. The base is 0.7 of a volt higher than the emitter because VBE is 0.7. So this voltage here must be 0.7 volts. And we were given VBB was 2 volts. So now we have the voltage on both sides of the resistor. We know the resistance value. We can calculate the current. IB, this is Ohm's law, is 2, the voltage drop across it, 2 minus 0.7 over 10K, which would be 130 microamps. Am I right? 130 microamps. Yes. IB is 130 microamps. Okay, so we've got IB. That was the first thing. IC is beta IB. So IC is 50 times 130 microamps. And we can get IC is 6.5 milliamps. So we got IB, IC, and now we want to figure out what VCE is. Remember, VCE is just going to be same notation, VC minus VE. We know VE is 0. So we really need to find VC. So I've got the voltage drop across RC is going to be 10 minus VC. Its current we've already solved for, 6.5 milli, and the resistance is 10K. So we can solve that for VC. 3.5 volts. So we want to check and see if it's actually in active mode after we got done with all this. So in active mode, we need the base emitter forward, which means VB, it's an NPN, so the base has to be NPN, has to be greater than the emitter voltage. VBE has to be positive. And we assume that. So yeah, that works. Let's make sure that it's actually the base collector, it's not in the other one, saturation, is reverse bias. So that would mean VB would have to be less than VC. And the base voltage, or we could add an E to that. We could just add a, that's like subtracting VE from both sides, which is 0 anyways. VBE is 0.7. We assume that. Our VCE is 3.5 minus 0 is 3.5 volts. So that checks out. We are in active mode. And then you go check the pins on the transistor and make sure that they're actually the right ones. It's a three-legged device. If it's late at night, looking at that picture on the data sheet, I'm sitting there holding the transistor and I'm putting it in exactly the same orientation as the picture, make sure the flat side is facing the same flat side, and then I look at it and I go, okay, base collector. The school I used to teach at, our labs ended at 11:30 at night. We were all pretty tired by then. I started teaching at 7:30 in the morning too, the 2 different jobs. So here's another one. We want to assume it's in active mode. We're given beta, and we want to find all the node voltages and currents. So this is 6 volts, that's VB. We can assume it's in active mode, so that gives us 0.7 of a volt between the base and the emitter. So this emitter voltage is going to be at 0.7 of a volt less than that, 5.3 volts. So VE, 5.3 volts. I know the voltage on both sides of the resistor. I've got the resistance value. I can find IE. It's just easier to write in caps. I know these are supposed to be lowercase. IE will be, this is Ohm's law, the voltage drop across it, 5.3 minus 0. V equals IR. Sorry, I equals V over R. R goes on the bottom, 3.3K. We can calculate IE. It is 1.61 milliamps. Well, that's just cute. IE. Okay. We have beta. We can calculate alpha. Alpha is beta over beta plus 1. So this is 100 over 101. What I did, I actually used alpha. I'm fairly proud of myself. 13. This is 0.99. And alpha was defined as being IC over IE. So I've got IE. I know that IC is going to equal 0.99 IE. And we can plug those numbers in, and our IC is 1.59 milliamps. Which means that IB is the difference between the two of them. IB, or we could use IB equals, what did I do? Yeah, I used IB was IC over beta. Oh, I'm looking at the wrong one. Oh, the numbers are the same. I use IB is IE minus IC. Either one should come up with pretty close to the same answer. 15.9 microamps. And then if we know IB, we know IC is 1.59 milliamps. Then the voltage at the collector right here, we can go back to Ohm's law again. 10 minus VC is going to V equals IR, 1.59 milli times 4.7 K, 7 K. And we can solve that for VC. This is number 13. VC, where is it? 2.53 volts. Okay, so we've got VC, we've got IB, we've got IC, we got IE, we have all the currents. We just want to verify it's in active mode. So I need the base emitter forward biased, we assume that. I need the base collector reverse biased, which means VB has to be less than VC. And is VB less than VC? What the heck was VB? VB is 6 volts, it's given. Is that less than 2.53? No, it's not in active mode. We're going to have to do something to fix that. And what we're going to do is this. It's the exact same circuit. Oh, thank goodness. It's the exact same circuit. I've just changed this to 4 volts. So this becomes, we'll solve it the same way, 3.3 volts. 3.3 volts over 3.3 K is going to give me IE is 1 milliamp. Yep. We can go through that same process again. Our alpha is still 0.99. So IC is going to be 0.99 milliamps. And IB is the difference between those two. So IB is 10 microamps. And then we can solve for VC. So if I've got 0.99 milliamps going through I'm frozen. I got 0.99 milliamps going through that resistor. I'm going to talk through it because I can't write. And then you can yell at me when I get back. My VC is going to be 5.35 volts. VBC, the base voltage is 4 volts. The collector voltage is 5.35 volts. That's negative, and we are in active region. So a lot of times you just have to tweak the circuits to get them in the right voltage range. What we used to do back in the day. Here comes part 3. And we've only got a couple more slides left.